Uh, Good morning, everyone. I want to welcome you to my lecture today. Of course, today we're going to focus on algorithm for partitioning clustering. I remember in the last class, I introduced you to clustering, and I talked about, I think I justify reasons why we need to do that. And of course, I remember I told you we got two ways of clustering. Okay, we got what we call the hard and soft. Of course, we talk about hard. Um, I remember I said you can only partition objects into non-overlapping groups, and of course with the soft, there's possibility that a particular object can be classified into more than one group. I remember I talked about probabilistic assignment. And I also mentioned that we got some partitioning clustering algorithm. Okay. And today, the focus is going to be on one of the partitioning algorithm that actually fall under hard clustering. We call it K-means. That will be the focus today. But let me tell you this. In the outline, I'm going to walk you through K-means. How do we use K-means as an algorithm to partition clusters? I mean, um, just like the brief introduction that I have, I welcome you to this lecture once again, where we're going to talk about algorithms for partitioning clustering. And of course, the focus is going to be on the K-means. Okay, so just like what I said, I'm actually going to introduce you to the basic fundamental principle of that, okay, including the algorithm, the application, and how we can evaluate the performance of the algorithm. Also going to highlight some limitations. And of course, lastly, I'm actually going to walk us through how that can be implemented in R. Okay, so before moving forward, I'm actually going to say, um, you remember the other time when I was introducing you to clustering, um, I said we got hard clustering and we got soft clustering, right? So the K means algorithm is classified under hard clustering because we actually when we are partitioning object into groups, okay, there's not going to be any room for overlapping, so the object can only be in one group. Okay, so that is exactly what we mean. So the common algorithm for hard clustering include the K-means that we want to talk about today. So there's also K-medoid, hierarchical clustering, and of course we got density-based partial clustering of application with noise. So I'm actually gonna walk you through all of that. So but like I said, the focus today is actually um you know K-means algorithm for clustering. Okay, so as a motivated example, the reason why we are partitioning is simply because we believe looking into the data structure originally there's heterogeneous. And of course, just like what I used to say, we live in a stochastic environment. We live in a probability space. We expect to have variations and reason why we're never going to be in the same category. So application of k-means now to this original data set will lead us to this. So what I'm trying to say here is that, okay, you know what? We've been able to partition the objects into two clusters, two categories. Okay, that's what we mean. And as you can see here, there's nothing like overlapping. So we use k-means for spherical clusters, and of course one of the limitation of k-means is that the moment you have non-spherical shape, may not be able to deal with that. Okay, so the goal of the of clustering in general, okay, is more or less that, okay, what am I going to tell the world if I've succeeded in partitioning the object into clusters? So the our intention is, our goal is to minimize the distance within objects, the way you're sitting down now, okay, that you sit down in group. Okay, if you take a look at this, if this is a person, is this another person? Of course, they are not sitting in the same spot, and distance still exists between them. But what we're trying to do is to minimize the distance within them. But if you take a look at this, at the same time, um, we're trying to maximize, the distance between clusters. Okay, some people are sitting in that table right now, some are sitting in that table right now, and of course, we want to make sure, there's a kind of, the distance between any two clusters is very much pronounced. Okay, so I want to go, I want to walk us through do we how do we actually use algorithm for k-means algorithm for clustering. Okay, so first I want to say that the algorithm, the k-means, what the k-means actually address, is a way to, you know, it's an unsupervised machine learning, where the goal is to make sure we partition, data set, into k distinct non-overlapping clusters, based on the inherent similarity, between data point. Okay, so we are doing all of this. We call it unsupervised learning because it work without predefined labels that I actually call the outputs. Okay, so this is a way we actually do it. If I want to use you the way you are sitting down now, okay, maybe you guys sit in groups, right? Okay, so since you sit in groups, so what we normally the first step in k-means clustering is that is what we call initialization, where we choose the numbers of clusters. Don't forget, the other time I actually said the domain knowledge is required. So a researcher will be the one that will decide on, okay, so what is the number of clusters that I actually want to work with. Okay, and after choosing that, okay, randomly from the data set, okay, then we're going to do a job, trying to assign, okay, we're actually going to assign each data point, okay, to the nearest centroid, okay, to the nearest, the centroid, we call the centroid, initially, you pick numbers, okay. I think I'm going to, demonstrate that to you now. So let's say in this class, you guys are sitting in group right now, okay, and I decided that, okay, or maybe initially before you were partitioned into this group, maybe I realized I'm actually I'm gonna have like 6 clusters, okay. Now having 6 clusters, if I measure your weight, okay, now by my estimation, you guys are 75 at the moment, okay. Now you're actually going to have different values for weight, right? So what I'm going to do, I'm actually going to randomly choose 5, okay. So maybe I'm just assuming now, okay, maybe I choose maybe somebody of 160 or somebody of 120, just assuming, um somebody of 60, um, somebody of 180, okay, and somebody, or maybe somebody of 200, okay, I'm just assuming, and somebody of 100, okay. So now what I'm actually going to do, okay, since I choose these numbers now randomly, okay, the remaining 60 or 69 numbers will be assigned to each of these, okay, using the Euclidean distance, okay. Now, after that, that's what I mean here. Now, the next thing we're going to do after the assignment, we're going to find the cluster mean, okay, mu1 here. We're going to find the mu2, okay, and so on like that. So the mean of each of the cluster is actually called the centroid. Okay, we call that centroid. Okay, now after calculating the mean, then we're going to assign the observation again. Okay, we're going to assign the observation to the cluster whose centroid is the closest. Of course, in statistics, we normally consider the position of observation relative to the mean. Okay, so and when we continue to do that, okay, we're gonna do that. We're gonna take note. It's that is converge when we realize that the mean doesn't change significantly. Okay, so we're gonna be updating that. So like I said, until the centroid, that I call the cluster mean, stop changing significantly, or the algorithm reaches a maximum number of iterations. Okay, is there any question at this time? Okay, so you all good, right? Okay, now um you know the next thing we want to talk about now is because we actually want to minimize you know uh the within variation, okay, the intra class variation, the variation within between objects in the same cluster. Okay, so we actually are going to have this as objective function. Okay, and if you take a look at the objective function now, we got with WIK, so which is going to be 1, for a particular data point if it belongs to cluster K. Otherwise, okay, that will be 0. Don't forget, using this clustering algorithm, there's nothing like overlapping. You get what I mean? There's nothing like overlapping. So can only be in one cluster. If you're in this cluster, then you are not going to be in the other one. And of course, don't forget, the mean also becomes a random variable, the mean of each cluster, because we compute the cluster mean, we update that, okay, and because of that, we got to a variable that we want to minimize this, and of course we actually looking for the optimal value for these two variable, and it's an optimization problem. Okay, because of that, you're gonna make use of the knowledge of optimization technique in mathematics, which is going to be differentiating that. We're going to differentiate that with respect to WIK. And after doing that, we actually getting the value of K. which is the optimal values of cluster that we minimize the interclass the variation I will talk about. Okay, so that's equation 2. Now, in equation 3, we're going to differentiate with respect to mu k. Don't forget, it's going to be a partial derivative. I got two parameters at a time. So, if I differentiate with respect to one parameter, I'm going to keep the other one at constant, and that's exactly what I'm doing now. So, after solving differentiating that and solve for mu k, we're actually going to have this. Okay, so after having that, the belief is, at the end of the day, we'll be able to get the optimal values of the parameter that will be able to minimize, the intra-class, variation that I talk about. Okay, so I briefly want to talk about the application of you know um the k-means algorithm. Okay, so when you want to talk about the application, it's actually very useful when you talk about image compression, okay, customer segmentation, anomaly detection, and document clustering. Okay, now the image I'm showing you now, okay, when I talk about image compression, okay, is there a way we can reduce the number of colors, okay, that we have in an image, okay, in such a way that we actually gonna cluster the pixel values, and we're still gonna retain the quality. Okay, it's still gonna be clear in a way. And some of you maybe are wondering, why do we need to reduce that? The reason why we actually need to reduce that, there's a lot of benefits that come with image compression. Okay, it's going to lead to reduced file size. Don't forget, imagine you have an image of 300 by 300 in dimension, and 300 times 300, that would be 90,000 pixels, and maybe each pixel has a triplet of color. Okay, maybe it has a triplet of color, maybe like red, like green, and blue. Okay, so imagine the number of pixels that we have, and of course it means we need more space when it comes to data storage. Okay, so because of that, we actually need to compress the image in such a way that when we compress it, we are never going to lose the quality, or even though I know that we're going to lose something, but it's not going to be much. Okay, so for faster loading times, okay, of image, okay, image with fewer colors, we load faster, okay, compared to the image with so many colors. Okay, then another thing is efficient storage, like I said the other time. So that's why I'm trying to give you this, this initial image, the original image, and this is after compression, using k-means algorithm. Okay, after compression, I can just decide to say, okay, I can decide, instead of so many pieces, is there where I can reduce this, where I'm actually going to partition the color. Maybe what I just wanted is 16 colors. Okay, I wanted 16 colors, and at the end of the day, so which means 16 clusters at the end of the day. So I'm actually going to have an image that has already compressed, so that's exactly what I mean. Now another example is document the another application of this is what we call when you process a document, that actually call document segmentation. Okay, so when you look at in the document segmentation, actually what normally happen is that we want to partition, maybe you have like 10 articles, okay, and you actually want to partition that maybe into 3 cluster. Maybe um you are just want to partition the 10 articles into 3 groups, and maybe um in each cluster, the first cluster is the one that is the article based, the one based on sports, and the other one based on politics, and the other one based on technology. Okay, so what I actually mean is that in each group, maybe the one that is based on sports, or maybe you want to talk about 2026 World Cup qualifier is one of the objects in the cluster. The other one may be maybe the Olympic games, and the other one may be a basketball game, of course, Minnesota Vikings. Maybe it's talking about a story that has to do with Minnesota Viking and Golden State Warrior. Okay, stuff like that. Okay, and of course, if you want to talk about the one in the politics, of course, maybe one's talking about the election, and the other one talking about the policy of the government, and so on like that. So that's, and actually is very, very useful, like I said, you know, um, in what I call document segmentation. And of course, in customer segmentation, you know, you want to be able to partition customers into 2 different groups: those who buy in high volume and those who buy in low volume. I remember, my wife, if a customer calling, she's already know, she used to say, oh, she's going to be excited because the customer used to buy in high volume. Okay, now this is the way it's actually going to work. Okay, because there's going to be a lot of you know pieces here depending on the dimension, and you decided to say, okay, you know what, I only need just 16 you know centroid. I need 16 clusters. Okay, and with the 16 clusters, and I use the algorithm, and you can see here, you see this is changing because we're going to set up iteration. Remember the other time when I was talking about optimization, of course, the number of iteration has to be greater than 1. So now that's what you see. Okay, so this is another visual way of explaining k-means. Okay, you can see the iteration going up and down. Okay, I mean, so you can see that. Okay, so after uh following the process of k-means algorithm, just like any other statistical model, okay, or algorithm, okay, we may want to know how can we trust algorithm, or how can we trust our model. And of course, if we want to do that, we use able. Okay, we use able, we use COT coefficient, and we use gap or statistic. Okay, by able, if you take a look at this, it's a graph of average expansion against the number of clusters. Of course, it's obvious that when cluster equal to 1, the average expansion is going to be so high because, I told you the other time, the when before you grow, before you partition into cluster, it's heterogeneous, so you expect the degree of disparity to be very, very high. Okay, and as you continue to increase in the number of clusters, you expect that to be going down. But where we are targeting now, if they take a look at this, we are targeting able. Okay, can you see that able right now that looks like an angle? We're going to trace it down. When we trace it down, we actually gonna say, okay, for this particular partitioning, choosing 3 clusters, that is actually going to be optimal. Okay, so that is exactly what we mean. Okay, so because at times we may not be able to figure out, it may be at times difficult to identify where the able is, and that is why we need to be able to have another way of judging that. okay, which another criteria, okay, and that very criteria right now is actually what we call the COT coefficient. Okay, so when you talk about COT or coefficient, this is a measure of the goodness of a clustering in such a way it actually evaluates how well each data point fits into that particular group that you assign the that particular cluster group you assign the data point, the object into compared to the neighboring clusters. And of course, this is going to come with values -1 to +1 that actually going to say, okay, the moment you have a +7 and above, that is actually strong, okay, and 0.5 may be referred to as being reasonable, and less than 0.5 and below, 0.25 and below, maybe kind of weak. Okay, so just wanted to take note of that. And if you take a look at what I'm trying to show right now, so this is actually pointing to 0.4. Okay, working with 5 clusters. Can you see that, right? 5 clusters, and you can see that's a value of 0.4. Okay, so with the gap statistics, you know, when you talk about the gap statistic, is another measure, okay? If another measure, that here we compare what we call the total within cluster variation, for different values of K. So which means what you're gonna do, you actually you can vary the values of K. You can first start with K equal to 2. Of course, you can start with K equal to 1. With K equal to 1, it means all of them, they are in the same category, which is not good, which is not going to be appropriate. So, because in the first place, there's, heterogeneous, within, so the heterogeneity is very high. That's why we need to partition that. And of course, with partitioning in group, okay, partitioning is going to start from 2, okay, and above. So you can actually consider when K equal to 2, you find the within the total within cluster variation, and for K equal to 3, you do the same. For K equal to 4, you do the same. So here the gap statistics is actually going to use the expected value, okay, that is determined by generating a large amount of reference data, okay, from a reference uniform distribution. Okay, so now with all of that explanation right now, I think I'm gonna walk you through how to implement K-means algorithm in R. Okay, even though I know my TA is also gonna walk you through all of that. Okay, so like I said, I'm gonna walk you through that now. But before moving forward, do I have anybody? Do you have any question? Is there anyone who need clarification or who want to ask question? Okay, so which means you guys, everyone is good. Okay, but like I said, do not hide your feelings. The moment you don't understand me, please make sure you ask question. Okay, so in now the very first thing we're gonna do is before we conduct analysis, the very first thing we do is actually to start with data preparation. Okay, don't forget, we want to learn from data. Okay, so I just wanted to know we're gonna have our data in form of rows and columns. Okay, in form of rows and columns. Okay, the rows will be represent the observations, and of course the columns will be variables. Don't forget, the variables could be one. Okay, the variable could be more than one, and don't forget we don't have output variable. There's nothing like outcome variable. We don't have a label. We don't have dependent variable. All the variables that we have, they are explanatory. Okay, and of course you're also gonna need to pay attention in case there's missing observation or missing value. All you need to do, you need to deal with that, whether by removing it or by estimating that. Okay, so you remember the last when I was walking you through converse function, the theory of converse function, and I said, one of the reason why at times we get algorithm or get stuck in local minimum, okay, is because of the fact that maybe the objective function is poorly scaled. Okay, situation where you got a lot of explanatory variables and they got different units. Okay, maybe one is talking about age, the other one is talking about income, the other one is talking about different, they are all in different units. For you to be able to be able to make the variables comparable, of course, they need to be scaled. Need to be scaled means you're actually going to standardize it, by trying to, get the z-score for each of that. We did that for comparable, purpose. Okay. Now, in the example, I'm actually going to use the data set on USA, USRS. Okay. This data set actually contain what I call statistics on arrest per 100,000 residents. Okay. For different crime variables like assault, murder, rape, you know, across 50 United States. Okay, so which means the 50 states in the US, they are going to be the observation. Okay, and additionally, the data set include the percentage of the population, residing, okay, in urban areas. Okay, so maybe the intention here is, okay, can we have a way to grow this state? Because we believe when it comes to crime variables, we believe, or crime rate, or whatever, we believe that some particular state, they actually going to be in the same group, okay, putting into consideration, okay, there are characteristics of interest. So we want to group 50 states in the US, okay, based on the crime variables. And for us to be able to do that right now, we actually want to use K means algorithm. Okay, you know, at times when you see police patrolling more in a particular state or in a particular district, okay, the reason why they do that is because they realize the crime rate probably is more in that particular district, and that's why it required they should have presence. Okay, now in R, if you need to be able to install and load some packages, for you to be able to, if you want to run the algorithm. Number one is tidyverse. That will be for data manipulation, because we actually gonna do a lot of manipulation here. And of course, in a cluster, that one actually to be able to get us ready for clustering algorithm. And of course, we need a factor extra. The factor extra is actually going to make us to have access to both the clustering algorithm and visualization. Of course, um, images are involved, and of course, we actually need a package, that will enable us, to do a lot, when it comes to the visual stuff. Okay, now let's get our data ready now. Okay, I want to load our data into R. Okay, so when you take a look at this now, I'm actually calling DF the name of my data now. So say okay, and of course I'm using the data that I call USRS. And now the next line is that, okay, you know what? There could be some missing values, okay, in the data set. Can we have a way to remove that or to do justice to that? Because when you have missing values, it could be problematic, or it could actually affect your analysis, the result of your analysis, and that is why we actually gonna deal with that. And of course, you remember I said something the other time that we actually need to scale variables, for effective comparison, and that's why you see the scale here. Now the next thing now, okay, so what we're gonna do now? Can we have a way to view the forces? Okay, that's what head means. We can also view the last six if you put tail. Okay, so right now, so take a look at this. Okay, don't forget, the variables are murder, assault, okay, urban population, and rape. Okay, and the values that you're seeing here has already, already been standardized. These are not the original value. And right now, we are only showing the state of Alabama, Alaska, Arizona, Arkansas, California, Colorado. Okay, this is a for six. We got a lot of them. Don't forget, we got 50 states in the United States. Okay, so Minnesota, it's not here now, but other states are there, except that we are only displaying just six right now. Okay, so the next thing that we actually want to do, we normally want to have a measure of distance. Can we have a way to make a picture of that? If you take a look at what we have now across all the states, okay, this is the way the image was initially, okay, and this is looking heterogeneous, okay, when you take a look at it right now. And what we need to do is like want to separate, want to actually cluster, we want to cluster this out. Okay, so I'm actually gonna start with K2, here that you see center, okay, here you see center equal to 2, right? Okay, the center equal to 2 actually means, okay, you know what? I want to start with two clusters. I want to start with two categories. Okay, so that's exactly what I mean. And if I start with two categories and I want to do the number of starts, I'm taking that to be 25. Okay, so take a look at that. This number of starts has to be more than one. Okay, now if I actually um click on K2 and it's going to run and automatically I'm actually going to have two clusters. Okay, it has grouped all the states in the United States into two clusters. And you know what, if you really want to know how many states in cluster 1 is 20 and in cluster 2 is 30, take a look at that, 20 and 30. Okay, adding them together that will be 50. And if you want to have access to the cluster means, okay, for each variable across, you want to know like this is the mean for murder for cluster 1, the mean for assault for cluster 1. When you are looking at the means of the crime variables for cluster 1, okay, it's actually that, and for cluster 2, it's actually that. Okay, so the next thing that we want to do, can we see the picture for these clusters, the two clusters? Okay, this is it. Take a look at that now. Okay, we got two clusters now. So these are not overlapping. If you take a look at that, this is a cluster plot. So what is trying to tell us now? Okay, you know what? In this category now, okay, putting into consideration the crime variables, we got Mississippi, North Carolina, South Carolina, all of that. Here, Michigan, and so on like that, in New York, Nevada, the Texas, and so on. And of course, here, you got the Connecticut, and others. Okay, this are in this category. Okay, so you may also want to generate what I call the ggplot, for that, where you want to look at the urban population and the murder. Take a look at that. Urban population and the murder. Okay, factor, cluster, Libre state. Don't forget. Okay, and this is the name of the data. Okay, now I want to base it on just two cluster. Don't forget, I use K2. My K2 equal to, is when I'm considering my center, having two center. You get what I mean? Okay, so when I do that, this is what you're gonna have. So take a look at that. So this is which we call a pairwise scatter plot. So this is a pairwise scatter plot right now. Okay, so I may not be able to know the number of clusters that work. Okay, I don't know whether it's going to be 2 or 3 or 4 or 5. And what I can do is I can also use the algorithm for 3 clusters, for 4, for 5, and take a look at the initial start. Okay, it's 25, 25. Now, when you do that, when you do that, that will give you an opportunity to be able to compare the total within, cluster variation. Okay, you actually gonna see that. Okay, now I know, and based on the K3 or 3 cluster, 4 cluster, 5 clusters, and I can also draw a picture. Okay, don't forget you need to load the the grid extra. Okay, now P1, P2, P3, P4. Now putting into consideration, K equal to 2, 3, 4, 5. Okay, now I want it to be in 2 rows that I can show the picture now. Oh my God, take a look at this. If this is when I got 2 clusters, this is when I got 3 clusters, this is when I got 4, and this is when I got 5. Okay, take a look at that. But when you take a look at this particular picture now, you may not be able to tell which one is optimal. Okay, unless you actually um, you know, trying to compare the total within variation, okay, before you be able to, or we make use of what I call the evaluation technique. Okay, now take a look at that. Now, like I said, showing you this picture now, where we got 2 clusters, 3 clusters, 4 clusters, and 5 clusters. We may not be able to tell what is the value of cluster that is optimal. And because of that, okay, what we're gonna do, we got method, okay, that we can use, okay, in determining the optimal clusters. Okay, we got able method, we got a sealed method, we got gap statistic, and let me tell you, at times they could actually there could be a conflict. Okay, there could be a conflict. Okay, because they also have their limitation as well. Okay, so if I want to write the code now for each of that, okay, for able, for sealed, for gap, what I'm actually gonna do, okay, because I want us to have the same values at the end of the day, we actually need to set seed and put in the same number. If everybody put the same number, okay, we are gonna have the same value. Don't forget, because of this guy here, this simulation is at random. The end starts, 25. So I just wanted to take note of that. So that's why we got to set seed, okay, the same seed, okay, for reproducibility. I think you all get it, right? Okay. Thank you so much for responding to that. Now, the first one here is going to be for able, okay, and the second one is actually for the slots, and the third one is for gap. Okay, so let's see what we're gonna have. Okay, so when you take a look at able right now, okay, you actually are gonna see that this guy support probably um that's happen here. But let me tell you this, another person could say, oh, is it right here? Okay, but what you can see right now, okay, you can actually see that initially when k equal to 2, okay, you see that what you have here, actually, if you take a look at uh the vertical axis talking about total within cluster sum of square, and don't forget we want to reduce that, and then when k let's say here, here is when k equal to 1, that would be huge, right? When k equal to 1, when everybody is in one group, okay, there is a high degree of heterogeneity. We expect the total within cluster sum of square to be the highest, which is this guy here. And by the time k equal to 2, you can see it go down, right? It go down, right? Okay, and when k equal to 3, you can see that when k equal to 4, okay, you can see that, when you take a look at all of these, there's possibility there may not be any significant difference. Okay, why we don't just want to waste our clusters. Okay, we don't want to waste cluster. We're looking for where it's actually going to converge. Okay, so based on this now, okay, we can say, okay, maybe the able actually occur at 4. Okay, so if you now go by way of this guy now, okay, if you go by way of this guy, you can see initially it started at 1, okay, and when it starts at 1, when it increase, okay, getting here now, okay, then it actually start going down. Okay, now when you take a look at what I have here, you could say, oh, maybe I should choose cluster equal equal to 2, or I just choose cluster equal to 3, you know, and so on like that. So take a look at that. Now, if you want to base it on gap statistic, because this has incorporated statistical idea, you know, more technical statistical idea, we can actually trust gap statistic. Okay, now when you take a look at this now, it's telling us the number of cluster equal to 4. As you can see, if you see the dotted line, it's actually saying, because when it starts increasing, okay, this is the point that is we start noticing a decrease. Okay, so that very point now, so it's like k equal to 4. So you can see 2 out of 4, two out of 3 actually agree that you know, the optimal number of clusters should be 4. Now that is what we're going to base our final model on. Okay, so now we're going to build our final model now, because the um you know, the selection criteria has already suggested optimal value, okay, of 4. Okay, now we're going to run our final analysis on k equal to 4. We're going to set it for reproducibility, and of course we're going to indicate all of that. Don't forget, we're choosing 4 now because of the fact that we've already checked that, you know, and the EBO and the like, you know, the model selection has pointed towards using 4 clusters. And at the end of the day, this is what I got. Okay, so cluster 1, cluster 2, cluster 3, cluster 4. We got some state here. How many states in cluster 1? 13. How many states in cluster 2? 16. How many states in cluster 3? 13. And how many states in cluster 4? It's actually 8. And of course, you can see the corresponding, you know, means, you know, the cluster mean, okay, for across the crime variable with the population. Okay, so we can also draw a picture based on the 4 clusters. Okay, now take a look at that now. So this is a code for that. You know, if you run that, so you're actually gonna get this guy now. So you can see the states here, you know, they are not the same. There's nothing like overlapping right now. Okay, I need you to take a look at all of these. Okay, so the 50 states in the United States have now been partitioned into 4 clusters. Okay, and in this cluster, of course, we got different number of states, and there's no overlapping at all. Okay, so this is where I'm actually gonna stop. Guess what? On Monday, I'm gonna go you know, into another clustering algorithm. This time around, it's actually gonna be okay. Medoid, you know, quickly gonna get there now, so that you can see what I'm talking about. Okay, so when you take a look at this, we just you know, we just discussed k-means clustering algorithm now, and you know, in this algorithm, the limitation here is you know, is using mean as the cluster center. Okay, and we all know mean is sensitive to outlier. Okay, you know, outlier, according to Benkamp in 1982, is a data point that is not consistent with the rest. And we all know the potential damage outlier could impose on the validity of whatever you know, result that we got. So, and that is why situation where you know, outlier is present among the objects for partitioning, you know, to be clustered, then of course using k-means may not be appropriate. But let me tell you this. You know, researchers have advanced their research, and of course we have some variants of k-means to address that challenge. But for now, okay, we want to believe, you know, the k-mean algorithm that I just presented today, you know, is actually it's only appropriate in a situation where there's no outlier in the data set. So where there's outlier in the data set, of course, the k-medoid is going to work, which I'm going to start with you on Monday. So on Monday, we're going to still continue with the clustering algorithm, and our next focus we actually will be on K-medoid. Is there any question before I go today? Okay, you're good, right? Everybody okay, right? Okay. Make sure you all stay safe. Have a lovely day. Have a lovely weekend too. Okay, bye for now. See you on Monday. Stay safe, everyone.